Episode 71, titled Wireless Architecture, APs versus Controllers and Division of Responsibility, the focus is on wireless as a shared medium that behaves differently than wired networking, and therefore benefits from coordinated control. Wired networks give each device a dedicated link, while wireless devices compete for airtime on shared radio channels, which makes consistency and coordination more important as environments scale. The exam tests wireless architecture by asking you to recognize where responsibility lives, what problems controllers solve, and when controllerless designs are perfectly adequate. The access point and the controller are not competing devices that do the same job, but complementary components with different roles. When you know what each is responsible for, you can infer why a roaming problem appears, why policy enforcement becomes inconsistent, or why great radio coverage still results in poor user experience. Wireless reliability also depends on the wired backhaul that feeds the access points, which means wireless design includes power over Ethernet budgeting and uplink capacity planning as well as channel planning. If you treat wireless as just another switch port, you miss these shared medium realities. This episode builds a clear division of labor model so you can choose the right architecture for different site sizes and constraints. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. An access point, often abbreviated as AP, provides radio access and bridges clients to the network, acting as the local entry point from wireless devices into the wired infrastructure. The access point handles the physical and data link layer interactions on the radio side, including beacons, association, and the radio parameters that determine how clients connect. It also bridges client traffic onto the wired network, placing it into the correct VLANs and forwarding it toward upstream services. In many designs, the access point also enforces certain immediate security controls at the edge, such as basic authentication exchange and encryption handling for the wireless link.
The exam expects you to recognize that the access point is the radio interface, meaning it is where signal strength, interference, channel selection, and transmit power directly influence client experience.
It is also where local failures appear first, because an access point with poor power over Ethernet supply, a bad uplink, or a congested channel will affect users even if the rest of the network is healthy. When you think of the access point as the device that converts radio connectivity into network frames, you can reason about both radio coverage and network connectivity. The access point is the local worker that makes wireless possible in a specific physical location. A controller centralizes configuration, roaming behavior, and security policy, providing coordination that becomes valuable when many access points must behave consistently. Centralized configuration means access points can share the same SSIDs, authentication methods, encryption settings, and client policies without requiring per-device manual tuning. Roaming support is a major reason controllers exist, because as clients move, they expect their sessions to continue seamlessly, and controllers can coordinate how access points handle handoff decisions and key exchanges. Security policy centralization also matters because wireless environments often require consistent segmentation, guest access rules, and access control decisions across many radios and buildings. The exam often tests controllers as the mechanism that makes large deployments manageable and predictable, not as a performance booster for the radio layer alone. Controllers can also support visibility, providing centralized logs, client tracking, and RF management insights that simplify troubleshooting. Central control is most valuable when your environment must behave like one coherent wireless system rather than a collection of independent hotspots. When you understand the controller as the coordinator, you can see why it becomes more important as the number of access points and clients grows.
Controllerless designs exist, and distributed control works fine in many environments, especially when the site is small and the operational requirements are modest.
In controllerless models, access points coordinate among themselves or operate independently with a shared configuration mechanism, such as cloud-managed configuration profiles. This approach can reduce on-premises complexity because there is no dedicated controller appliance to deploy, patch, and maintain. For small sites, the number of access points is limited, roaming complexity is lower, and the cost of centralized controller infrastructure may not be justified. Distributed control can still provide consistent SSID and authentication settings if configuration is managed centrally through management tools, even if roaming optimization is less sophisticated than a controller-based design. The exam expects you to recognize that controllerless does not mean unmanaged, because distributed designs can still have strong centralized configuration through management platforms. The key is that the coordination function is either simplified, distributed, or provided through a different mechanism, and the suitability depends on site scale and user mobility patterns. When you choose controllerless, you are choosing simpler operational footprint at the cost of some advanced coordination features. For many small environments, that trade is reasonable and effective. Controllers are typically the right choice for large sites that need consistent roaming behavior, because roaming problems scale with user density and physical movement across many access point cells. In campuses, hospitals, warehouses, and large offices, clients move across floors and buildings while maintaining real-time sessions such as voice calls, video meetings, and critical application connections. Consistent roaming requires coordinated handling of authentication, key management, and policy so the client does not experience repeated re-authentication or session drops during movement. Controllers also help maintain consistent radio settings and can coordinate channel planning and power adjustments across many access points, which reduces co-channel interference and improves overall stability. The exam often frames this as many users and many access points, and the correct architecture tends to include controllers because manual per-access point management becomes error-prone and roaming experience becomes inconsistent without coordination. Large sites also often require centralized security policy enforcement for guest networks, device onboarding, and segmentation, which controllers support well. When you choose controllers, you are choosing predictability at scale, which is a major availability and user experience advantage. The key is that wireless at scale is a system, and controllers help make it behave like one. Standalone access points are often the right choice for small sites with simple needs, where the primary goal is coverage and basic secure access rather than seamless roaming across large physical areas. A small branch office may have only a few access points and relatively low mobility within the space, making advanced roaming coordination less critical. In these environments, the operational simplicity of standalone access points can be a strong advantage because there is less infrastructure to maintain and fewer moving parts that can fail. Standalone does not mean unplanned because you still need consistent SSID naming, secure authentication, and basic channel planning, but those needs can be met with simpler management approaches. The exam expects you to match architecture complexity to site needs, and small sites often benefit from simpler designs because they reduce maintenance burden and reduce the chance of misconfiguration through unnecessary features. Standalone access points can also be easier to replace in the event of failure because a single unit can be swapped without impacting a centralized control plane. When you choose standalone access points, you are optimizing for operational simplicity while meeting basic wireless requirements. The correct choice is the one that meets requirements without overbuilding. Wireless reliability depends heavily on backhaul requirements because access points are only as good as their wired uplinks and power delivery. Backhaul is the wired connection from the access point to the switching infrastructure, and it must have sufficient capacity, low error rates, and stable power delivery to support the wireless load. Power over Ethernet matters because access points often rely on it for power, and insufficient switch power budget can cause access points to reboot, disable radios, or operate in reduced function modes. Uplink capacity matters because an access point can provide strong radio coverage and still deliver poor throughput if the uplink is saturated or limited by an older interface speed. The exam tests this because it reinforces that wireless is not purely a radio problem, and that many wireless issues are actually wired constraints, such as oversubscribed uplinks or inadequate PoE. Backhaul also includes VLAN configuration, trunking, and quality of service policies that ensure wireless traffic is handled correctly as it enters the wired network. When you design wireless, you must design the wired support for it, including power, uplink speed, and redundancy where required. A well-designed radio layer cannot overcome a weak backhaul, and the exam expects you to recognize that coupling. A scenario where roaming failures suggest controller tuning needs highlights why controllers matter for session continuity in mobile environments. Users may report that calls drop when walking between areas, that video meetings freeze briefly during movement, or that device connectivity pauses when transitioning between access points. These symptoms often indicate that roaming handoff is not optimized, that authentication transitions are slow, or that policy is inconsistent across access points.
A controller can coordinate roaming behavior and apply consistent settings so handoffs are faster and more predictable, but the controller must be tuned to match the environment's mobility patterns and client mix.
The exam expects you to interpret roaming failures as an architecture and coordination issue rather than as a raw signal strength issue alone, especially when coverage appears adequate. Roaming tuning also interacts with the wired network because delays in reaching authentication services or policy servers can exacerbate handoff times. When roaming fails, the design question is often whether control is centralized appropriately and whether policies are consistent, not just whether there are enough access points.
This scenario is a cue to think about the coordination layer.
Inconsistent SSID settings across access points are a common pitfall because they cause client confusion and unpredictable behavior that appears as intermittent connectivity. If one access point advertises a different SSID name, different authentication method, or different encryption settings, clients may connect to the wrong network or fail to roam properly. Even subtle differences, like mismatched security options or different VLAN mappings for the same SSID, can cause clients to drop and re-authenticate repeatedly. This inconsistency often arises in controllerless environments where configuration drift occurs, or in mixed environments where some access points are managed differently than others. The exam tests this pitfall because it reinforces the need for centralized configuration and standards, regardless of whether a controller exists. Inconsistent SSIDs also complicate troubleshooting because the behavior can vary by location, device type, and time, making it feel random. The correct mitigation is to standardize SSID definitions and authentication policies and to enforce them through a management system that prevents drift. When SSID consistency is maintained, clients experience smoother connectivity and roaming.
Another pitfall is insufficient uplink capacity that bottlenecks good radio coverage, which produces user complaints that look like wireless problems, even though the radio layer is performing well.
An access point may have strong signal coverage and low interference, yet users experience slow downloads, high latency, and poor video quality because the uplink to the switch is saturated or limited.
This can occur when a high-density access point serves many clients but has only a low-speed uplink, or when many access points share a single uplink from an intermediate switch that is oversubscribed. It can also occur when backhaul is constrained by quality of service misconfiguration that deprioritizes wireless traffic or fails to prioritize real-time flows. The exam expects you to recognize that throughput and experience depend on the whole path, and that uplink constraints can dominate even with excellent radio planning. Diagnosing this requires looking at switch port utilization, errors, and uplink aggregation points, not only at wireless metrics.
When you see good coverage but poor performance, backhaul is a likely suspect.
Wireless architecture must therefore include uplink capacity planning as a first-class concern.
Quick wins include standardizing SSIDs, channels, and authentication policies, because consistency reduces client confusion and makes performance more predictable. Standardized SSIDs ensure clients see the same network name and security options across the environment, supporting smooth roaming and reducing reauthentication events. Standardized channel planning reduces co-channel interference and improves airtime efficiency, especially in dense environments where overlapping coverage can create competition on the same channel. Standardized authentication policies ensure that access decisions and segmentation behave the same regardless of which access point a client uses, which improves both security and user experience. The exam often rewards these practices because they reflect operational maturity and because they are effective regardless of whether you use controllers or distributed control. These quick wins also simplify troubleshooting because you reduce the number of variables that can differ between areas. Monitoring and periodic configuration audits support these standards by detecting drift before it becomes a user-impacting incident. When wireless is standardized, it becomes a manageable service rather than a collection of unique configurations. A useful memory anchor is radio at AP, coordination at controller, because it captures the division of responsibility in a way that aligns with exam scenarios. Radio at AP reminds you that the access point handles the physical wireless interface, including coverage, channels, and local client association. Coordination at controller reminds you that controllers centralize configuration, roaming behavior, and security policy across many access points, making large deployments consistent. This anchor helps you diagnose problems because it tells you where to look first based on the symptom. If the problem is local coverage or interference, it is likely at the access point and radio layer. If the problem is roaming consistency, policy drift, or site-wide configuration behavior, it is likely in the coordination layer. The anchor also supports architecture selection because large sites need coordination more than small sites. When you apply the anchor, controller decisions become straightforward. To apply the decision, imagine choosing architecture for a campus with many users, many access points, and frequent mobility across buildings. In that environment, consistent roaming behavior and consistent security policy become critical because users expect sessions to persist as they move, and support teams need predictable behavior across large areas. Controllers provide centralized management that reduces configuration drift and improves the ability to tune roaming and security policies across the fleet. The wired backhaul must also be designed with sufficient PoE budget and uplink capacity to support the density, because controller-based coordination does not fix power shortages or saturated uplinks. You would also want standardized SSIDs and authentication across the campus, so clients experience one coherent network rather than many micronetworks. The exam expects you to choose controller-based architecture for this type of environment because the scale and mobility demands make distributed manual control risky. Your justification should tie to roaming consistency, policy centralization, and operational manageability. When you can state those reasons clearly, you demonstrate the intended selection logic. To close episode 71, titled Wireless Architecture, APs versus Controllers and Division of Responsibility, the key is to understand that access points provide the radio interface and bridge clients into the network, while controllers centralize configuration, roaming behavior, and security policy to make large deployments consistent. Controllerless designs can work well when sites are small and needs are simple, because distributed control reduces infrastructure complexity while still enabling basic secure connectivity. Controllers are the better fit for large sites where consistent roaming and policy enforcement are required across many access points and many users. Wireless reliability depends on wired backhaul, including stable PoE delivery and sufficient uplink capacity, because weak backhaul can bottleneck excellent radio coverage. Roaming failures often point toward coordination and tuning needs, while inconsistent SSIDs and policy drift create client confusion and intermittent behavior. Standardizing SSIDs, channels, and authentication policies is a practical quick win that improves stability regardless of architecture choice. The memory anchor that radio lives at the access point and coordination lives at the controller keeps the division of labor clear during design and troubleshooting. Your rehearsal assignment is a design justification drill where you take a site description and explain why you chose controllers or standalone access points, including how backhaul and policy consistency support that choice, because that drill is how you demonstrate wireless architecture reasoning the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.